Welcome to section 14.1b. All right, gentle people, what I want to do is I want to start talking about this molecule right here. What you guys will notice is the central carbon is SN3. There's no lone pairs, so what you guys would say is the angle between here and here and here is 120 degrees. So let's go ahead and try to bring hybridization and orbital overlap theory to try to describe how we can get these angles. Now remember, if I don't have anything hybridized, the angle of my orbitals are 90 degrees. So I can't use unhybridized orbitals to get this picture. Now if I hybridize and I make sp3 orbitals, well, my angles are 109.5 with the new sp3 orbitals that I generate. But this still doesn't get me to 120 degrees. So what I need to do is I need to hybridize in a different way. So again, I'm going to take my unhybridized orbitals, I'm going to mix them together in a certain way to try to get to that 120. And the way we do this is we create new orbitals called sp2 orbitals, and these ones will get me my 120 degree angles that I desire. So here's what I'm going to do. I have an s orbital, I have a p orbital, another p orbital, and another p orbital. So in this case, what I'm going to do is I'm going to only take two p orbitals and mix them with my s orbital. So when I do this hybridization, what I generate is an sp2 orbital, an sp2 orbital, and a third sp2 orbital. Now, one of these p orbitals I did not touch, and so it is going to remain just like it is. So again, to go back to my analogy, I have Sprite, Pepsi, Pepsi, and Pepsi. I take these 4 glasses of soda, and this time I'm only going to take 1 glass of Sprite, 2 glasses of Pepsi, and mix them together. Once I mix them together, I pour out this mixture into 3 new glasses, and that gets me a mixture of Sprite and 2 parts of my Pepsi, or an sp2 soda. Now this glass of Pepsi that I didn't use, well, it wasn't part of my mixture, so it still remains a glass of Pepsi. And so this is the same thing that we're going to do with orbitals. I'm going to take an s orbital, a p orbital, a p orbital. I'm going to mix these waves together, and I'm going to generate 3 sp2 orbitals, or 3 sp2 waves. The p orbital that I didn't touch remains the same, and it is going to maintain its properties. You guys can see this mixture taking place on this slide. So here's my S, P, and P, and I'm going to go ahead and mix them. Now an sp orbital is going to look like another lopsided dumbbell, where there's a big lobe and a little lobe. So what you guys see here is I generate my sp2 orbitals. There's 3 of them, and each one of these are in a different orientation. If I were to combine all 3 of these into one picture, what you guys would see is this picture right here. Just focus on the yellow lobes. So this is an sp2 orbital, this is an sp2 orbital, and this is an sp2 orbital. It turns out when I do this combination of orbitals, my sp2 orbitals are 120 degrees apart from each other. This purple orbital that you guys see here, well, that's the 1p orbital that I did not use. And so what you'll notice is that this p orbital right here is going to be 90 degrees from these sp2 orbitals. All right, gentle people, to use my models again. So I'm going to start out with a central atom. It has an s orbital, but I'm going to just go ahead and represent my p orbitals. So again, I have my pz going up and down, my px going left and right, my py going in and out. So this is showing you guys 3 p orbitals. Remember, a p orbital is a dumbbell, So every p orbital has 2 lobes. So what I'm going to do is I'm going to hybridize these p orbitals. So I need just 2 of these p orbitals. So let's do this p orbital that's going left to right. And then let's take the p orbital that's going in and out. And I'm going to mix these 2 p orbitals with an s orbital. Now if I go ahead and do that, what I generate is this picture right here. So each one of these white paddles represents an sp2 hybrid orbital. What you guys will see is those sp2 hybrid orbitals are 120 degrees away from each other. Now, there is one p orbital that I didn't hybridize, and that's the one that's going up and down. So the one p orbital that I didn't use, so this one going up and down, still remains on the atom itself. This p orbital is 90 degrees away from the white sp2p orbitals. And so this is what happens when you hybridize as sp2. All right, let's go ahead and summarize what happens here. So if I look at these carbons right here, these carbons are SN3. So around both of these carbons, what I expect are angles of 120 degrees. Now remember, 120 degrees, I need to hybridize my orbitals. I can't use the unhybridized orbitals because those are at 90 degrees. I can't use sp3 because those are at 109.5. So what I need to do is I need to mix an s orbital and I have to put 2 of the p orbitals together. So I have to put spp together to get sp2. These orbitals are at 120 degrees. Once I get those 120 degree angles, I can perform my orbital overlap and I can form my bonds. So it's only when I generate this hybrid orbital that I get the correct geometry predicted by VSEPR theory and what I observe in real life. Now understand, one of the p orbitals was unhybridized, so it maintains its properties. So that p orbital is going to remain the same. Now for this particular example, I use the 2s and the 2p because that's the valence orbitals of carbon. But let's go ahead and take this a step further and kind of describe what's happening here with this double bond. So if we look at each carbon, the carbon on the left-hand side is sp2 hybridized. So what that means is one of my p orbitals is unhybridized. So I'm going to put this in purple. 2 of my p orbitals with an s orbital are going to be hybridized. So I'm going to generate sp2 hybrid orbitals. So one is going to go to the right. One is going towards you guys like this. And then one is going to go backwards like that. And I'm going to do the same for the other carbon. I got my carbon in the center. I got an unhybridized p orbital. And I got my sp2 orbitals 120 degrees apart from each other. So one is going to the right. One is going towards you guys. And one is going backwards like so. So let's go ahead and use the model. And what I'm going to go ahead and show you is I'm going to bring hydrogens to overlap on each one of these orbitals to form bonds. And then I'm going to go ahead and describe the bond in the middle. All right, so here's one of my carbons, the one on the left. Here's one of the carbons, the one on the right. And so what you guys can see is the white paddles. Each white paddle represents an sp2 orbital. Purple paddles represent that one p orbital. So what I'm going to do is I'm going to bring a hydrogen over. Now a hydrogen is just going to be an s orbital, and so I'm just going to go ahead and overlap one of these orbitals, and then I'm going to form a bond by doing that overlap. And I'm going to do these for each carbon. So what you guys will see is that I've put 2 hydrogens on each carbon because each one of those guys were overlapped with those sp2 orbitals. Now what I'm going to do is I'm going to bring these carbons together. So if I bring these carbons together, what you guys will see is that I form this overlap between this sp2 orbital, that white paddle, and this white paddle, this other sp2. So I'm going to go ahead and form a bond there. Now I'm going to make this bond super short because I want to emphasize something that's going to occur here. So I'm going to bond these two things together. And when I bond these two things together, what you guys will notice is another overlap happen. The other overlap that you guys will see is that my p orbital is overlapping with another p orbital. So remember, this right here is one p orbital. Here's the second p orbital made out of two paddles. And you'll see that there is an overlap between those two. Now remember, when I overlap orbitals, that means it forms a bond. This overlap between my purple paddles is the double bond. And so if I wanted to go ahead and show it bonding, this is what the double bond looks like. Now I want you guys to be careful. The top and the bottom, that is the second bond in this molecule. The first bond is right here, this short bond that I use, which was the overlap between the sp2 orbitals. I'm going to go ahead and show you guys that first bond in the double bond. I'm going to remove some paddles for clarity. So I've removed the paddles. So this is the first bond in the double bond. And both of these gray connections here represent the second bond in the double bond. So if I wanted to overlay them, this is what the bonding looks like between the two carbons. So the first bond in the double bond is just in the middle. The second bond is above and below that first bond. Now, what we're going to do is we're going to go ahead and describe the symmetry of this bond. Now to do this, the first thing I want to do is I just want to look at each one of the bonds. So let's take a look at the first bond in the double bond. So that's this connection right here. Now what you guys will notice is that this bond right here is perfectly symmetrical with the bonding axis. And what I mean by the bonding axis is if you draw a line between the two nucleuses and you rotate around that line, you can see that this bond right here is perfectly symmetrical. On the other hand, if I were to draw a line between the two nucleuses, so a line like that, and I were to go ahead and rotate this, the second bond in my double bond is not symmetrical. What I mean by that is you can tell that I'm spinning this because the bond goes in and out, it goes away from you, towards you, so you can tell that I'm spinning this molecule. Whereas this one, if you just focus on the bond itself, you really couldn't tell that I'm spinning it. What you would see is that this rod right here is perfectly symmetrical. Now there's consequences to this symmetry. So let's take a look at this bond in the center. So I said that this was a symmetrical bond along the center. If I have a symmetrical bond, this is called a sigma bond. A sigma bond, what you guys will notice is I can twist or rotate the molecule and I will not break a sigma bond. I can easily twist around it. But let's go ahead and look at a non-symmetrical bond. So if I look at this, this was my non-symmetrical bond, and so this was the second bond in my double bond. Let's go ahead and see if I can twist my molecule. If I go ahead and twist my molecule, what you guys will see is I almost break that overlap between the p orbitals. And so what happens is when I have a non-symmetrical bond, we call this a pi bond. And I'm not allowed to rotate around a pi bond because if I try to do that, I will snap the bond. So the consequence of a pi bond is it will lock the molecule into a certain configuration. All right, gentlemen people, let's go ahead and re-emphasize this pictorially. So what I had between my carbon and carbon is I overlap these two sp2 orbitals. This creates a sigma bond. This is the first bond between the atoms. And a sigma bond is symmetrical with the axis of rotation. That means that I can have rotation around a sigma bond. Now, the other overlap that I had was between these two p orbitals. So in purple is the second bond in the double bond. This is not symmetrical with the bonding axis. And what that means is I cannot rotate around it, because if I try to rotate around it, I'm going to snap this interaction in purple. And that's why we care about the classification of a bond and how we break down a double bond. All right, gentlemen people, let's revisit this slide. Now what I want to do is I want to bring a new molecule to your attention. Let's say I have a carbon that's triple bonded to another carbon, and I have hydrogens on each side. Now if I look at this carbon on the left-hand side, it is steric number 2 without any lone pairs. So the angle right here is 180 degrees. And so let's go ahead and look at my list and see if anything works. So I can't use the unhybridized because those are at 90 degrees. I can't use sp3 hybridization because that's at 109.5. And I can't use sp2 hybridization because that's at 120 degrees. So I need a new hybridization to accommodate 180 degree angles. So what I'm going to invoke is something called sp hybridization. When I hybridize as sp, this is appropriate for that molecule that I just drew out for you. So how does this work? Well, I'm going to take an s orbital, and then I have my p orbitals, but this time what I'm going to do is I'm only going to use an s and a p orbital. So when I do this hybridization, I'm going to generate two sp orbitals, and then two of my p orbitals I did not use, so they are going to remain untouched and they're going to translate over. So again with my analogy, Sprite, Pepsi. 1 glass of Sprite mixed with 1 glass of Pepsi redistributed equals a 50-50 mixture of Sprite and Pepsi. I had 2 glasses of Pepsi that I didn't touch, and so they are just going to be the same and left over. Again, I'm mixing waves. An s orbital mixed with a p orbital gets me an sp orbital. Any orbital that I did not hybridize remains the same wave and translates over. So you guys can see this in this picture. I take an s orbital, a p orbital, and I mix them together. So again, an sp orbital looks like a dumbbell that's lopsided. One lobe is bigger than the other. So when I mix this s and p orbital together, I generate these two sp orbitals. These are going to be orientated 180 degrees away from each other. So if we look at this orange to this orange, this is 180 degrees away from each other. Now remember, I had p orbitals that I didn't touch. These p orbitals are going to remain 90 degrees apart from each other, and they're also going to be 90 degrees away from my sp orbital. So again, to summarize, SN2, I need 180 degrees for my orbitals. So what I'm going to do is I'm going to mix one s orbital with one p orbitals. This is going to get me two sp orbitals, and two of my p orbitals are going to be unhybridized. Everything in this one is going to be 90 degrees except for the sp orbitals, which are going to be 180 degrees apart from each other. All right, Chem 1A, we are going to work some problems out using this in the next couple of lectures. So be sure to check this out so you can see how to use this information. Other than that, remember to stay safe.